Hello students, welcome to the first session of the chapter Heterocyclic Compounds. It has 4 sessions and this is the first session in which you can find the definition for heterocyclic compound, classification with examples, orbital structure, resonance and aromatic character of furan, pyrrole, thiophene and pyridine. Then Huckel's rule of aromaticity and also preparation of pyrrole from acetylene and from ammonium mucate. Coming to the definition of heterocyclic compound, you will be knowing about that, which is heterocyclic compounds are cyclic compounds which contain one or more heteroatoms such as oxygen, nitrogen or sulfur as ring atoms. Normally, in organic compound, the normal cyclic compound, the ring will be made up of only carbon. Whereas in heterocyclic compound, at least one ring atom will be any other heteroatom. Like apart from carbon, it will be oxygen, nitrogen or sulfur. These are abundant in plant and animals. For example, in alkaloids, dyes, drugs, proteins, vitamins, etc. These heterocyclic compounds are abundant. It is found to be seen in plants and animals. Then generally heterocyclic compounds are aromatic in nature. Then coming to the classification of heterocyclic compound, based on the number of ring atoms including the heteroatom, we can classify them into 3. The first one is 5-membered heterocyclic compound. Here, the 4 carbon atoms and 1 heteroatom such as oxygen, nitrogen or sulfur will be there. In 5-membered heterocyclic compound, there will be 4 carbon atom and the 5th one will be any heteroatom like oxygen, nitrogen or sulfur. For example, furan. This is furan. Here this is a 5-membered ring. One of the heteroatom is oxygen and the other 4 carbon atoms are present in the ring. This is pyrrole, is again 5-membered ring where there are 4 ring carbon atoms and the final heteroatom is nitrogen. And this is thiophene where the heteroatom is sulfur and all other parts of the ring is substituted by carbon. 6-membered heterocyclic compounds with 5 carbon atoms and nitrogen as heteroatom. There will be in 6-membered 5 will be carbon atoms and the 6th one will be the heteroatom. For example, pyridine, we have 5 carbon atoms in the corner and the heteroatom is nitrogen. And pyridine, it is again nitrogen but it is saturated. This is unsaturated and aromatic, whereas pyridine not saturated and it is not aromatic. It is saturated and it is not aromatic. Third classification is fused heterocyclic compound where a 6-membered ring may be fused with a 5-membered or 6-membered ring. One ring will be the 6-membered ring. Along with that, there will be another ring which can be 5-membered or it can be 6-membered. Here in indole, at this position there should be nitrogen, then only it will become indole. That is indole. Indole where a 6-membered ring is fused with a 5-membered ring where this position there should be one nitrogen, that is indole. Then in quinoline, 2 6-membered rings are fused together. One is benzene and other one is pyridine. So when pyridine and benzene are fused together, we get quinoline. And the third compound is isoquinoline. It is another version of quinoline where nitrogen atom is at the 2nd position. That's it. So these examples we can give for fused heterocyclic compounds. So heterocyclic compound based on the number of ring atoms including the heteroatom, we can classify them into 3 categories. One is 5-membered heterocycle, then 6-membered heterocycle and the fused heterocyclic compound. Now, coming to orbital structure, resonance and aromaticity of furan. Furan compound will take and we'll try to explain the orbital structure and aromaticity. We'll see whether furan is aromatic or not. See that this is the structure of furan. Furan, we have seen already that it is a 5-membered ring. And in the 5-membered ring, there are 4 carbon atoms, 1, 2, 3, 4 carbon atoms and 1 oxygen atom. all the carbon atoms are in sp2 hybridization. It is sp2 hybridization, and oxygen is also in sp2 hybridization. So here what's happening, because of sp2 hybridization, it will be having 3 sp2 hybrid orbitals, and all the 3 sp2 hybrid orbitals are used to form bond with the neighboring carbon atoms and oxygen atoms, along with one hydrogen atoms. Here all at the all carbon atom there will be hydrogen atom except on oxygen. Now, what is left out on carbons? Now, one unhybridized p orbital is left out, which is not involved in hybridization. That unhybridized p orbital has one unpaired electron. It has one unpaired electron. So, all the carbon atom will be having a p orbital with unpaired electron, as well as oxygen will have 2 p orbitals with lone pairs of electron. So what will happen is all these orbitals, 5 orbitals of carbon, or 4 orbitals of carbon altogether, and one of the lone paired orbital of oxygen will overlap together to produce delocalization. So how many total electrons are there? All these electrons are considered to be, as they are overlapping laterally, they are considered as pi electron cloud. So there will be pi electron cloud above and below the ring. It will produce delocalization, and that will give aromaticity for the molecule. So to have aromaticity, it has to satisfy one criteria, one rule. What is the rule? That is Huckel's rule. According to Huckel's rule, the molecule should be planar. It is planar because all the atoms are undergoing sp2 hybridization. So the molecule is planar. Now there should be delocalization in the molecule. There is delocalization in the molecule. Now the number of pi electron in the delocalization cloud should satisfy Huckel's number. What is Huckel's number? It is 4n plus 2. 4n plus 2. So this, how many electrons we get here? It is 1, 2, 3, 4 and 2 electron. This lone pair will not contribute for delocalization. It is away from the plane, so it will not contribute. So only 2 electron will contribute from oxygen. So together we have 6 pi electrons in the delocalization cloud. The 6 is a Huckel number or not? Yes, 4 into 1 plus 2 will give 6. There are 6 electrons, 6 is a Huckel number. So it satisfies all the criteria of Huckel's number, and we can say furan is aromatic. This is the explanation of the previous slide. And along with that, furan is also resonance stabilized because of the delocalization, as there is alternative double bond and a lone pair of electron on oxygen atom which can involve into delocalization. It will enter into resonance and we get many resonating structures. So whenever there is resonance in a molecule, it will add up to stability. So the structure of furan is highly stabilized due to resonance. Now, how can we explain the orbital structure, resonance and aromaticity of pyridine? Pyridine, we have seen it is a 6-membered heterocyclic compound. There are 1, 2, 3, 4, 5 carbon atoms and 1 nitrogen atom. So whenever there is a heteroatom, that position is considered as first position. That is why we are starting the numbering from here. So altogether there are 6 atoms on the ring. Now, how about the hybridization of all these atoms? Nitrogen as well as all the carbon atom will undergo again sp2 hybridization. Just like I have explained in the case of furan, here also all the all the sp2 hybrid orbitals will be used to form bonds with the neighboring carbon atoms as well as nitrogen atom and hydrogen atom, and completely the sp2 hybrid orbital will be used for bond formation, sigma bond formation. What is left out? Again, on carbon atom, there are unhybridized p orbital with unpaired electron. And on nitrogen, again, there is one electron, one unhybridized orbital which contain unpaired electron, and another one contain lone pair of electron, but that will be apart from the plane, which will not contribute for delocalization. So from nitrogen, only this orbital which contain one electron will be contributing for resonance. So altogether, how many electrons we have in delocalization cloud? Here we have 1, 2, 3, 4, 5, 6. We have 6 electrons in the delocalization cloud, and again it will be aromatic because it is again planar molecule. Hybridization is sp2, it is planar. Then there is delocalization in the molecule. Then also the Huckel number 6 it satisfies, and so pyridine is again aromatic. How about the resonating structures of pyridine? Again, there are 3 double bonds in conjugation along with double bond lone pair of electron on nitrogen, but though that lone pair will not contribute for resonance. It is not required. So it will not contribute. Apart from that itself, the double bonds are enough because there is alternative double bond. When there is alternative double bond, there is no need of lone pair to take part into resonance. So all these structures we get for pyridine for resonating structures, which will add up to the stability of pyridine. Now, how can we prepare the first heterocyclic compound, which is pyrrole? Pyrrole can be prepared by 2 methods. One is from acetylene. Acetylene and ammonia, when passed through red hot tube to get pyrrole. When we pass through red hot tube, pyrrole will be formed. This is acetylene. 2 molecules of acetylene will combine with ammonia molecule, and that mixture will be passed through red hot tube. We get pyrrole. Other method of preparation is from ammonium mucate. Ammonium mucate is heated with glycerol, forming the corresponding acid, that is mucic acid, which undergoes dehydration, then decarboxylation, and then ring closure by the reaction with ammonia, forming pyrrole. This is ammonium mucate. Ammonium mucate on heating with glycerol molecule. What is glycerol? CH2OH, CHOH, CH2OH. That is glycerol. It will combine. So it will undergo reaction, first dehydration, then decarboxylation, and finally ring closure to form the molecule pyrrole, along with the formation of carbon dioxide molecule, water molecule, and ammonia molecule. So these are the 2 methods by which we can prepare pyrrole. So students, through this session, you would have learned about the definition for heterocyclic compounds with examples, then classification of these compounds based on the number of ring atoms with suitable examples again. Then how can we explain the aromaticity of heterocyclic compounds based on Huckel's rule, and how can we write the resonating structures of all these compounds. The same explanation what I have given for pyrrole is applicable for thiophene as well as furan. Because all these compounds are 5-membered ring, there are 2 double bonds and there will be 1 lone pair of electron on the hetero atom. So all the 3 compounds the aromaticity can be explained in the similar way. Then we also have seen how we can prepare pyrrole from different methods.